Okay, in this lecture, we can look at one of the results which we have discussed in the previous lecture. So what it says is, if we have k distinct eigenvalues of A, which belongs to, for a matrix A, C, and cross N, then if xi's are the eigenvalues associated with eigenvectors associated with eigenvalue lambda I, where I is varying from 1 to k, then the set of vectors x1, x2, etc., xk form a linearly independent set. Okay. This is the so if there are k distinct eigenvalues, there are there exists k linearly independent eigenvectors. This is basically the gist of the result. So how we're going to prove this is by using contradiction. Okay. So initially, we suppose that there are k distinct eigenvalues, and we'll suppose that the xk vectors are linearly dependent. Okay, we assume that it's linearly dependent. Then, if they are linearly dependent, there exists a linear combination with at least uh, r number of non-zero coefficients. So if there are k vectors, or not all of them need not be linearly dependent, but at least k of them, so at least r of them are linearly dependent. Okay. So what I'm trying to say is, for linearly independence, what we have to show is if there is alpha 1, we are taking a combination of alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha k xk is equal to 0. If they're linearly dependent, some of them are actually non-zero, is what we know, right, for linearly dependent vectors. Let's say R is a number which are actually non-zero. So alpha 1 x1, alpha 2 x2 plus etc. alpha r xr is equal to 0, where alpha not equal to 0. This is by definition, we are trying this, and r is greater than 1. Now, for this vector, we pre-multiply with a. So a into 0 on the right side is again 0, which is a 0 vector. It's a vector. And on the left side, you have alpha 1, ax1, alpha 2, ax2, plus alpha r, axr. So since these are eigenvalues, a into x1 will be equal to lambda into x1. Similarly, a into x2 will be equal to lambda into x2. And a into xr will be lambda r into xr. Sorry, it's not lambda 1 x1, lambda 2 x2, etc., lambda r xr. Fine. So this is 2, and we've already had this equation, right? We mark this equation alpha 1 x1 plus alpha 2 x2 plus alpha r xr as equal to 0 as 1, and this alpha 1 lambda 1 x1, alpha 2 lambda 2 x2, alpha r lambda plus etc. plus alpha r lambda r xr is equal to 0 as the second equation. Now we substitute, we subtract, we multiply the first equation by lambda r and subtract 2 from that. So if we subtract, what we get is lambda alpha 1 into lambda r minus lambda 1 into x1 plus alpha 2 into lambda r minus lambda 2 into x2 plus alpha 3 into x1 etc. plus alpha r minus 1 plus lambda r minus lambda r minus 1. The last term will go to 0 because it has lambda r minus lambda, so that will go to 0. Right. So here, lambda r minus lambda 1, etc., lambda r minus 1 can't be 0. Why it can't be 0? Because we've already said that all these eigenvalues are distinct. If they're distinct, then the difference between them can't be 0, since lambda. So all the coefficients remain non-zero. which means that we can have a small linear combination. So initially we assume that there are non-zero coefficients, alpha 1, alpha 2, etc., alpha r. But now we have lambda r minus lambda 1, etc., lambda r minus lambda r minus 1, which is r minus 1 number of coefficients, right? So even with r minus 1 coefficients, we are able to uh, represent a linearly dependent set. But we already assumed that well, R is the least least number of coefficients for representing a linear dependent set. So this is a contradiction. So this can't be true. The assumption that these vectors are linearly dependent are wrong. So they are linearly independent. That ends the proof.